Hello viewers, in today's session we are going to discuss one important and conceptual problem from differentiability of functions. And in this class we are going to discuss this problem in which we have to discuss the differentiability of this mod function, that is f of x is equal to mod of x plus 3 at this point, that is x is equal to minus 4. Right now, see, the modulus function is a continuous function for all real numbers, but it is not a differentiable function. Right, suppose we have a modulus function of this type, say f of x is equal to mod of x plus a. Right now, this mod function is continuous for all values of x, but this mod function is not differentiable at this point, that is x plus a is equal to 0, that is x is equal to minus a. Right, so for this point x is equal to minus a, this function is not differentiable, but it is continuous at this point x is equal to minus a. Now if we have the function of this type, say mod of x minus a, then this function is continuous for all values of x for real numbers, and this function is not differentiable at this point, that is x minus a is equal to 0, that is x is equal to a. Right, so in this problem we have the function mod of x plus 3. So this function is continuous for all values of real numbers, but this is not a differentiable function at this point, that is x plus 3 is equal to 0, that is x is equal to minus 3. So this is the only point where this function f of x is not differentiable, and it is differentiable for other points. Right, so here we are taking this point, that is x is equal to minus 4. So this function is going to be differentiable at this point, x is equal to minus 4. But here we'll see how we can prove that this function f of x, that is mod of x plus 3, is a differentiable function at this point. So the derivative of this function, it exists at x is equal to minus 4, but at x is equal to minus 3, this function is not differentiable. So with the help of the concept of left hand derivative and right hand derivative, we'll prove that this function is differentiable at x is equal to minus 4. So by the definition of differentiability of functions, we know that if the derivative of a function is to exist at some given point, then the left hand derivative must exist and it must be finite. And similarly, the right hand derivative must exist and it must be finite, and both the derivatives must be equal to each other. Right, so if we have a point, say x is equal to a, then the left hand derivative at this point must be equal to the right hand derivative at this point, x is equal to a. So in this case, first we'll find out the right hand derivative, and we'll find out the left hand derivative, and we'll see that both the derivatives are equal to each other. So now let us first find the right hand derivative. So the right hand derivative is given by this notation, that is f prime of a, and here we write a positive sign, and we write limit h tends to 0 f of a plus h minus f of a divided by h. Now here a is minus 4, so we can now write limit h tends to 0 f of 4 minus 4. Here a is minus 4, so minus 4 plus h minus f of minus 4 divided by h. So now the value of f of minus 4 plus h can be obtained by replacing x by minus 4 plus h. So we have mod of minus 4 plus h over here, plus 3, then we have f of minus 4, that is mod of minus 4 plus 3, and here we have h, right? So now this is limit h tends to 0, and 3 minus 4 is minus 1 plus h. Then here we have mod of minus 1, here we have h, right? So now we can rewrite this expression as limit h tends to 0 mod of h minus 1, and mod of minus 1 is plus 1, so we have simply 1 here, and here we have h. So now here we have mod of h minus 1, right? Now from the definition of mod function, see, a mod of p is given by positive p whenever p is greater than 0, and mod of p is 0 when p is 0, and mod of p is negative p when p is less than 0, right? Now see here, we have h minus 1. So if we take p is equal to h minus 1, then h is infinitesimally very small as compared to 1. So h minus 1 is less than 0. So this is a negative quantity. So here a mod of p is equal to negative p will apply this property of or this part of this definition. So mod of p is minus p when p is less than 0. P is h minus 1. H minus 1 is less than 0. H minus 1 is a negative quantity, right? So mod of h minus 1 is equal to negative of h minus 1. That is 1 minus h. So here we have limit h tends to 0, and here we have 1 minus h minus 1 over h. Now this one and this one get cancelled. We are left with limit h tends to 0 minus h over h. So this is the limit h tends to 0, and h get cancelled. We are left with minus 1. So this is minus 1 because this is independent of h. So limit h tends to 0 minus 1 is minus 1. So the right hand derivative of this function at this point is equal to minus 4 is minus 1. So now we can write here f prime of minus 4. Here we write a positive sign, so the right hand derivative is equal to minus 1. So now let us find out the left hand derivative. So the left hand derivative is given by f prime of a. Here we put a negative sign, and this is given by this limit h tends to 0 f of a minus h minus f of a divided by minus h, right? So this is limit h tends to 0 f of a can be replaced by minus 4. This is minus h minus f of minus 4 divided by minus h, right? Okay, so now let us find out the value of f of minus 4 minus h, which can be obtained by replacing x by minus 4 minus h. So we have mod of minus 4 minus h plus 3. Then here we have f of minus 4, that is the mod of minus 4 plus 3. And here we have minus h. So this is limit h tends to 0, and this is 3 minus 4 is minus 1. This is minus h, and here we have mod of minus 1, and this is minus h. So now here we have a mod of minus 1 minus h, right? So again we'll make use of this definition of mod function. So minus 1 minus h is again less than 0, right? Because here we have negative sign, here also we have negative sign, and h is a positive quantity, right? H is infinitesimally very small, but it is greater than 0. So minus 1 minus h is less than 0, that is this quantity is negative. So again mod of p is equal to negative p when p is less than 0. So mod of minus 1 minus h is equal to negative of minus 1 minus h. So this is 1 plus h. So minus minus plus minus minus plus, right? So mod of minus 1 is equal to 1. So now this limit is limit h tends to 0, and we have 1 plus h minus 1 over minus h. So now here we have limit h tends to 0, 1 and minus 1 get cancelled. We have h over minus h, and h get cancelled. So we have limit h tends to 0 minus 1, that is minus 1. So the left hand derivative of this function at this point, that is f prime of minus 4, here we write a negative sign, and this is equal to minus 1, right? So we see that the left hand derivative and the right hand derivative both exist, and they are finite at this point. X is equal to minus 4, and both are equal to each other. So we can write left hand derivative is equal to right hand derivative. Hence the derivative of this function, that is f prime of minus 4, it exists. It means this function is differentiable at this point. X is equal to a, that is x is equal to minus 4, and f prime of minus 4 is given by the common value, that is the left hand derivative is minus 1, the right hand derivative is minus 1. So here we have minus 1. So we can say that this mod function mod of x plus 3 is differentiable at x is equal to minus 4. Hello viewers, in today's session we are going to discuss another important conceptual problem from continuity of functions related to greatest integer function. So here we are going to discuss one important problem where we have to discuss the continuity of this function f of x, which is equal to greatest integer of x minus 1 at x is equal to minus 3, right? And here we can see that we have to discuss the continuity of this greatest integer function at this integral point, that is minus 3 is an integer, right? So let us start. So to discuss the continuity of a given function at some given point, what we do, we find out the right hand limit, and then we find out the left hand limit, and then the value of the function at the given point. So here if we take the point in general as x is equal to a, then we find f of a. And if these three quantities exist and they are finite and equal to each other, then we can claim that the given function, say y is equal to f of x, is continuous at x is equal to a. So the right hand limit, the notation for right hand limit is limit x tends to a. Here we put a positive sign. This is f of x, and then the left hand limit has the notation limit x tends to a minus. Here we put a negative sign, and here we have f of x, and this is equal to f of a. So in this problem we'll find out the right hand limit, then left hand limit, then f of a, and then we'll see whether these three quantities exist and finite, and whether these three quantities are equal to each other or not, right? So let us first find out the right hand limit. So the right hand limit is given by a limit, then we have x tends to minus 3, and we put a positive sign here, and the function f of x is greatest integer of x minus 1, right? So now what we will do, here we have x is equal to minus 3. So when we approach x is equal to minus 3 from the right of x is equal to minus 3, we reach a point that is very close to x is equal to minus 3, and this point may be taken as minus 3 plus h, where h is a positive quantity which lies between 0 and 1, and h is infinitesimally very small, right? And similarly, when we approach towards x is equal to minus 3, from the left of x is equal to minus 3, we reach at a point that is minus 3 minus h. So to get the right hand limit, we'll now transform this limit in terms of h by substituting x is equal to minus 3 plus h, where h is infinitesimally very small and it is a positive quantity, and when x approaches to minus 3, then h tends to 0. So the right hand limit is now equal to limit h tends to 0. For limit x tends to minus 3 plus, we can now write limit h tends to 0, and for x we can now write minus 3 plus h, and here we have minus 1. So now we'll solve this limit, and we have greatest integer of minus 4 plus h. So minus 3 minus 1 is minus 4. So this can also be written as limit h tends to 0, and here we can write h minus 4. Now see, whenever we come across with the limits involving the greatest integer function or fractional part function or the signum function, we cannot directly substitute h is equal to 0. So what we will do, see here we have greatest integer of h minus 4. So if we take the real number line, and here we have minus 3 and here we have minus 4, right? So here we have minus 4 plus h, and h is a positive quantity. So when we add h to minus 4, then this quantity, it lies between minus 4 and minus 3, right? So minus 4 plus h is greater than minus 4, but it is less than minus 3. So when we add h, which is a positive quantity, to minus 4, then minus 4 plus h is greater than minus 4, but it is less than minus 3. So minus 4 plus h, it lies somewhere between minus 4 and minus 3, and by the definition of greatest integer function, the greatest integer of minus 4 plus h is equal to minus 4, right? So now we have limit h tends to 0, and here we have minus 4, so this is equal to minus 4. So the right hand limit of this function at x is equal to minus 3 is equal to minus 4. So now let us find out the left hand limit. So the left hand limit is limit, and here we write x tends to minus 3, and we put a negative sign here, and f of x is greatest integer of x minus 1, right? So when we approach towards x is equal to minus 3, from the left of x is equal to minus 3, then we take x is equal to minus 3 minus h, and remember h is a positive quantity and it is infinitesimally very small, and h lies between 0 and 1, right? So when x approaches to minus 3, then h approaches to 0. So let us now write this limit in terms of h, and we have limit h tends to 0. We have greatest integer of x minus 1. X is minus 3 minus h, and here we have minus 1. So we have limit h tends to 0, greatest integer of minus 4 minus h. So minus 3 minus 1 is minus 4, and this is greatest integer of minus 4 minus h, right? Okay. So now again let us consider this real number line, and here we have minus 5. Now see, we have minus 4 minus h, and h is a positive quantity and minus h is a negative quantity. So when we add minus h to minus 4, then this quantity, it lies between minus 5 and minus 4. So minus 4 minus h, it is greater than minus 5, but it is less than minus 4. So this quantity, that is minus 4 minus h, it lies between minus 5 and minus 4, or in other words we can say that minus 4 minus h is lying between minus 5 and minus 4. And by definition of greatest integer function, the greatest integer of minus 4 minus h is equal to minus 5. So now this limit, that is left hand limit, is equal to limit h tends to 0, and here we have minus 5. So this is equal to minus 5 because here we do not have the quantity which depends on h, so this limit is equal to minus 5. So the left hand limit is equal to minus 5, and now the value of the function, that is f of a, that is f of minus 3, is equal to greatest integer of minus 3 minus 1, taking x is equal to minus 3. So we have greatest integer of minus 4. Minus 3 minus 1 is minus 4, and we know that the greatest integer of any integer is the integer itself. So this is equal to minus 4, right? So the value of the function, that is f of minus 3, is equal to minus 4. So from this discussion, we have seen that although the right hand limit and the left hand limit both exist, and they are finite, right? But the right hand limit is not equal to the left hand limit, that is minus 4. That is right hand limit is not equal to the left hand limit, that is minus 5. So we can conclude that the limit x tends to minus 3, f of x, that is limit x tends to minus 3 and greatest integer of x minus 1, it does not exist because the right hand limit and the left hand limit are not equal to each other. So the limit of this function at x is equal to minus 3 does not exist. Hence we can say that the function f of x, that is greatest integer of x minus 1, this function is discontinuous at x is equal to minus 3.